In this video, we're going to talk about probability assignments, starting with the concept that the probability of an event occurring is always between 0% and 100%, or between 0 and 1 if you're using a fraction or decimal. A 0 probability means that the event is certain to not occur, like when rolling a 6-sided dice, the probability of rolling a 7 would be 0. 100% probability means that the event is certain to occur. This is the formal definition for probability, or the formula that you could see in the formula booklet. It says that the probability of A, which means the probability of event A, is equal to the number of elements in A divided by the number of elements in the sample space. So written out, that's the number of elements in A, you'll count them up, how many things are in A, divided by the number of elements in S, S being all of the possible outcomes for the experiment. You won't often use this formula, you'll just use common sense to set up probability fractions, but this is the formal definition. So here's some simple probabilities that you may be asked to calculate. So we're going to find the probability of the following events occurring for the random experiment rolling a fair dice. So you probably wouldn't list out this sample space because it's pretty well known, but if you were, capital S equals the set 1, 2, 3, 4, 5, and 6. So those are the possible outcomes when rolling a fair dice. So when asked to calculate, for example, the probability of rolling an odd number, an even prime number, an odd prime number, or a number that is either prime or even, you could lay out the set for each of these events and then count up the number of elements. So for example, in A, the probability of rolling an odd number, well, that event, let's call it A, includes 1, 3, and 5, because those are the odd numbers that are a subset of S. And then you can count up that there are 3 things in A, there are 6 things in S, and so the probability of A is 3 over 6, which reduces to 1/2. I tend to leave probability answers as reduced fractions. But realistically, you're not going to take all the time to write out the set that way. If you can just count it in your mind, how many elements from the sample space do meet that criteria, you can come up with the probability a bit faster. So rolling an even prime number, the only even prime number is 2. So that's a 1 out of 6 chance that you'll roll an even prime number. For C, rolling an odd prime number, well, that's 3 and 5. So 2 out of 6, which reduces to 1/3. And no, I only said 3 and 5, and that's because 1 is not a prime number. And then D, rolling a number that is either even or prime, either prime or even. So that includes the 3 and the 5, as well as the 2, and also the 4 and 6 because they're even. So that's a 5 out of 6 probability that you'll roll a number that's either prime or even. So now to dive into the probability rules, and these will stretch across the chapter. We'll do the first 4 today. So the rule 1 is that the probability of any event takes a value from 0 to 1. So this is basically the same as the first concept that you wrote down in these notes, but written symbolically. And the second rule, similarly, is sort of foundational. The fact that all possible outcomes together have a probability of 1. So this is like, what's the probability of rolling a 1 through 6 when you roll a 6-sided dice? It's going to be 1, because the probability of getting something in the sample space is going to be 1. Or the probability of getting a 1, a 2, a 3, a 4, right? If you calculate the probability of getting a 1, it would be a 1/6. The probability of getting a 2, that would be 1/6, and so on. And all those 1/6 added together will equal 1. Okay, and then an interesting rule that has some new vocab in it. So for disjoint, also known as mutually exclusive events, those are just vocab words that mean the same thing. And these are events where there's no overlap between the 2 events. So it might be the even numbers and the odd numbers, right? Nothing would be in the overlap region if we had those 2 events on a Venn diagram. And so for that type of event, this formula is going to hold true. The probability of one or the other happening is equal to the sum of their separate probabilities. So basically, in this little picture, the probability of getting something from A or B, if you call these circles A, B, is going to be whatever the probability of the A circle is plus the probability of the B circle. So written out formulaically, that's this. And it has a name. This formula is called the addition rule for mutually exclusive events, which is exactly what it is, that you can add the probabilities of A and B together if A and B are mutually exclusive in order to figure out the probability of A or B. And then one last rule before we head into some examples, the probability of an event not happening. The fastest way to figure out, what's the probability that you will not roll a 2 is going to be to subtract that number from the total overall set. So 1 minus the probability of the event actually happening. And these would be called complementary events, like rolling a 2 and not rolling a 2 would be complementary events. Even numbers and odd numbers would be complementary events, because if you're not one, then you are the other. And the formula would be that the probability of not A, that's how you will read this, is equal to 1 minus the probability of A, or vice versa. And you can represent that on a Venn diagram. If there's just one event, A, then everything outside of the A circle would be the complement to A. If you did have two circles, it gets a little bit more visually confusing, right? If you have an A and a B circle. But if the A circle is the one on the left here, then not A does still include everything outside of the A circle, regardless of whether it falls in the B circle or not. You can almost just ignore the B circle when trying to figure out what's in not A. And now for some examples. So here we have data collected about traffic violations. And it shows the probabilities that the offender you pull over is going to be in one of the following age categories or age groups. And it's important to establish that these age groups, like 18 to 20 or 21 to 29, these are mutually exclusive events. There's no way that a single offender could fall into more than one of these at the same time, looking at the way that the breakdowns are. So these are mutually exclusive categories. And so that means that we're allowed to use the mutually exclusive addition rule if we need to in order to figure out combined probability. In the questions below, what is the probability that the offender is, if you pull over an offender, in the youngest age group? Well, that's just, can you read the table, right? So the youngest age group is going to be a 0.06 probability. Probability that the offender is between 21 and 40. So this is basically the two middle age categories. And because they're mutually exclusive, I can just add those two probabilities together to figure out the probability of being in the 21 to 40 age group, which is going to be 0.76. And then the last one, the probability of being younger than 40, and that's going to include the first three groups probabilities. So basically the total from part B plus the added 0.06 for a 0.82 probability. So we are allowed to add the separate probabilities together because these are mutually exclusive. Similarly, when people create cell phone codes to log into their phones, these are all the options for your first digit, right, 0 through 9, and the probability is highest that a person will choose a 1, followed by a 2, followed by a 3. Those are the three most common answers. And then all of the other ones decreasing in probability down to the 9, with 0 being the most improbable or the least probable. So we've got some probability questions to answer here. Again, these are mutually exclusive because there's no way that the first number of your cell phone code could be two of these at the same time. It's going to be one thing from this table. So the probability of the first digit being 1, well, that's just going to be 0.3. I actually have all these answers down below. It's a little bit disorganized here. There it is. The probability that the first digit is 1 is going to be 0.3. That's just from reading the table. The probability that the first digit is going to be more than 5 includes the probability for 6, 7, 8, and 9. Because they're mutually exclusive, we can add them together and get this total of 0.221. And the probability that the first digit is an odd number, so that means I can add together the probabilities of 1, 3, 5, 7, or 9, and determine that the probability of the first one's odd is 0.603. And then to launch into part B, find the probability that the first digit is 1 or greater than 5. So because these are mutually exclusive, in order to figure out the probability of A or B happening, I can add together. And I already know the probability of 1, and I already know the probability of greater than 5. That's A and B as defined above, so I can just add those together. What is the probability that the first digit is? The last one, probability that the first digit is an odd number or a number larger than 5. And for this one, you're going to have to think a little bit. You can't just add, because odd number and number larger than 5 are not independent events, are not mutually exclusive events, right? Because there are some numbers that are both odd and larger than 5. So there will be an overlap there. So I can't apply the addition rule for mutually exclusive events. Instead, I'm going to look to the table and just add together the probabilities of all the odd numbers plus the additional numbers greater than 5. So all the odd numbers are shown there in black, plus the 2 in purple are the 6 and the 8. So the probabilities of the even numbers that are larger than 5. and then that total is equal to 0.721. All right, and then we have the first taste of a tree diagram. A tree diagram is a visual way of representing simple events, and you want to use these if there are a lot of possible outcomes. So like these are not ideal for rolling a dice and trying to figure out the probability of getting a 2 or a 3 or a 4, because you end up having to create a branch for every possible outcome, and rolling a dice has 6 outcomes. So you don't want to necessarily use a tree diagram. It won't save you a lot of time. And you definitely want to use a tree diagram if there's not a lot of outcomes and there's one event followed by another, like flipping a coin and then flipping a coin again. Because you can follow along the branches of the tree in order to figure out the probabilities of all these certain outcomes. So we'll look at an example here, one tree diagram, and then we'll do these throughout the rest of the unit as well. So 2 fair dice are rolled, 1 red and 1 blue. And I did just say that it's not ideal to use a tree diagram for a dice. However, when we look at the questions that are going to be underneath this screen shade, you should notice something. So the questions that are going to be asked of us are all about rolling a 6 or not rolling a 6. And so I can create this tree diagram where the 2 possible outcomes are rolling a 6 or not rolling a 6, right? They do not need to have equal probabilities on a tree diagram. And so because there's one dice being rolled followed by another, it lends itself to this tree diagram setup. Let's see if I can scroll up here. Where this is the first event. It's rolling the first die, right? I have 2 options. I could be rolling a 6 or I could be rolling not a 6. And you'll notice I've labeled the probabilities right along the arrows. Probability of rolling a 6 is going to be 1 out of 6. The probability of not rolling a 6 is going to be 5/6. And then if I get a 6 on the first roll, now I'm going to roll the second dice. And again, I have the options of 6 or not 6. Same thing, if I rolled a not 6 on the first dice, now I'm going to roll the second one, and my options are still 6 or not 6. What's cool about a tree diagram, a couple things, but one is that it shows every possible outcome if you follow along the branches, right? First top branch is 6, 6. Next one is 6, not 6. The one below that is not 6, 6. The final branch is not 6, not 6. And then you can multiply along the branches in order to calculate the probabilities of each of these overall outcomes. The probability of getting a 6 is the 1/6 from the first branch, and then 1/6 from the second branch, multiply them together to get 1/36. And then the same goes for every other possible path on the tree diagram. In the end, you get these 4 probabilities of all the final outcomes, which will add up to 1. And now we can answer questions like a double 6 is rolled. What's the probability there? Well, that's the 1/6 times 1/6. So the probability of getting a double 6 is 1 in 36, because there's lots of other things you could get, right? 3 and 4, 1 and 5, 5 and 5, 4 and 2. So many other things. The probability of getting a 6 followed by a 6 is very slim. It's only 1 in 36 chance. Probability of getting no 6s, this is just going to be the not 6 category, and this is pretty common, that I would roll 2 dice and not get a 6 on either one of them. The next one's talking about the probability that exactly 1 6 is rolled, and so that's going to be this 10 over 36. It's coming from exactly 1 6, meaning I roll a 6 on one dice and not a 6 on the other dice. And there's actually 2 pathways that meet that condition. Each of them is 1/6 plus 5/6. So it's 5/36 that you get either a 6 not 6 or a not 6/6. And so then you can add those 2 probability pathways together to figure out that there's a 10 in 36 chance that you'll get exactly 1/6. And then the final probability question here is talking about the probability of getting at least 1/6. So as you can see on the picture below, that includes all the pathways that are not the bottom one. And so the way I calculated this probability, rather than to add those 3 branches together, was to just do 1 minus the not 6 probability. And that's how you get the probability that you'll get at least 1. It's going to be 1 minus the probability of none. And that is all.